Welcome back to another Chemistry Mole video. Here we're going to be looking at carboxylic acids. So we're going to be looking at four key features of carboxylic acids here. So first thing is the solubility of carboxylic acids in water. Then we'll look at their dissociation in water. We'll look at the stability of the carboxylate ion that forms. And then we're going to look at the strength, or we're going to compare the strength of some different carboxylic acids and look at the types of reactions that they will undergo. So the first thing to look at here in the top left hand corner is I've drawn any carboxylic acid with an R group. So we could have methanoic acid, so just a hydrogen here, or we could have a CH3 group for ethanoic acid. And I've drawn a water molecule here as well. So the first thing that we need to do is understand the type of interaction that a carboxylic acid has with water. And hopefully you should be able to spot already that we've got a hydrogen bond that's going to form here, because we've got a hydrogen here between two highly electronegative elements, these two oxygens here. So the first thing you need to be drawing is your dipoles. So you need to draw all of the dipoles here. So the two delta negative oxygens on the carboxylic acid, the delta positive hydrogen here on the OH group, and then you also need to do the same thing here on the water molecule as well. So we've got the two delta positive hydrogens here, and I would also draw the lone pairs of electrons on the oxygen and show that that one is delta negative. In between the two, you then want a straight dotted line that shows for a 180-degree bond angle between these two bonds here. That's our hydrogen bond there. So make sure you label the hydrogen bond in your molecule. So that there explains the solubility of a carboxylic acid in water. That's a simple diagram, you just need to learn it, you need to show that. Our second thing that we need to look at here is our dissociation of carboxylic acid in water. So it's a really simple thing. You add a carboxylic acid to water, the carboxylic acid is going to break apart and it's going to release one of the H+, it's going to release its H+ here from the OH group. And it's going to produce a carboxylate ion, and we've dissociated, we've lost a proton. Now, if you've looked at the acids unit already, you'll realise that the more the equilibrium lies to the right, the stronger the acid will be, because more H+ ions have been dissociated into solution. The more the equilibrium lies to the left, the less dissociation there has been, and the weaker the acid would be. Now we're going to have a look here in a little bit more detail, the stability of this carboxylate ion. So this doesn't really show the full picture of a carboxylic acid or the carboxylate ion from a carboxylic acid. Now, in order for the carboxylate ion to become more stable, the electrons, so the two p orbital electrons, so we've got the double bond here, and one of the lone pairs of electrons here on this oxygen, these will they will delocalize across this bond, similarly to what you would see in benzene, and the charge is spread out. So you've got the sideways overlap of the p orbital electrons, and the electrons are dissociated, delocalized across this whole bond here. So the electrical charge is spread across these two oxygens. Now, obviously, because the oxygens are more electronegative than the carbon, that means that the electrons will spend more time around the two oxygens because they're drawn more towards these two oxygen atoms here. But the key thing to note is that we've got a delocalization of electrons here across this bond. And that's going to be important for understanding the strength of our carboxylic acid in a moment, because it's to do with the stability of this carboxylate ion, which determines how strong how strong the acid is actually going to be. So let's look at some examples here that I've drawn here at the bottom. I'm going to draw the delocalization of all of the electrons across these bonds here, just to show the electrical charge is being spread. Now there are key features we need to look at here. So three different examples. Now I'm going to explain this looking at these two examples here. So this first example, what we've got is we've got a highly electronegative element, we've got chlorine, a strongly electronegative element attached to the second carbon here in the carboxylic acid chain. Now what that's doing, that is actually pulling electrons, it's withdrawing electrons from the carbons on this part of the molecule. So the chlorine is withdrawing electrons away. Now the effect that that's having, it's making the ion is more stable, and that is because the negative charge here is less. So the negative charge is smaller. Now with a lower negative charge, that means it's less attracted to the H+ ions that it can dissociate. So there's less attraction to the H+. Now with less attraction to the H+, that means it would dissociate more H+ in solution, so this would be a stronger acid. So just quickly to recap, chlorine's pulling electrons away, stabilising this ion, making this group here, this delocalization lower, because the electrons are being pulled away, so the negative charge here is smaller. That's going to make it a stronger acid because there's less attraction to the protons. It can dissociate more protons into solution. If we have a look at this particular example, we're going to have the opposite explanation. The CH3 group here is donating electrons. So the CH3 group is pushing electrons in towards the carbon here. The negative charge is going to get stronger. The ion is less stable. With a less stable ion, we've got a greater negative charge. So they've got a stronger negative charge. Didn't mention here that there's less negative charge. So on this one here, this negative charge is now stronger. Therefore, there's greater attraction, so more attraction to H+ ions. And therefore this is going to be a weaker acid because it's less able to lose these H+. It's less stable, so it's more attracted to the H+. And that would be true, so if we moved on and we had an ethyl group, we'd have more electrons being pushed onto the carbon. That ion would be less stable, this would be more negative, and the attraction to the protons would be greater. So there are three types of reactions that we need to understand. So we've got the reaction between an acid and a metal, where we get the metal salt and hydrogen produced. We also need to know the reaction between an acid and an alkali, where we're going to get salt and water produced. And we'd also need to know the acid and carbonate reaction. This is one of the most important ones here, because this is the test for a carboxylic acid. So adding sodium hydrogen carbonate and getting some effervescence. So let's have a look at some examples of these different reactions. So we go through the first one here. If we're going to pick an acid, let's just pick methanoic acid. So we've got methanoic acid and a metal. So we're picking here a pretty reactive metal. We've got sodium, it's quite high up in the reactivity series. We produce our carboxylate ion. So this is our methanoate ion. And it's going to be attracted to the sodium ion, which is produced. And then we're going to get some bubbling in our solution, and we're going to get some hydrogen gas that's going to be produced. Just need to make sure that we balance this equation. So we can test the gas being produced here, the lit splint, collect the gas, lit splint, and then we get the squeaky pop test. So that's the first reaction. So we're going to need a pretty reactive metal to be able to react with our carboxylic acid here, because they're quite weak acids. You need something fairly high up in the reactivity series to do this. Our next example, so let's just say ethanoic acid is our example. And we'll pick ourselves a strong alkali, so potassium hydroxide would be a good example here. This time we're going to produce a methanoate ion, an ethanoate ion. This was the methanoate ion, this is the ethanoate ion. We've got our potassium ion that's going to be attracted to this, and then we're going to produce some water out of this reaction here. That equation should be balanced, so we've got 3, 4 hydrogens there, another one there, there's 5, 3, 4, 5 hydrogens here, 1, 2, 1, 2, so the carbons are balanced, and then the oxygens, we've got 3 oxygens in total, 1, 2, 3, 1, 2, 3, so we're fine with our balancing on that equation there. Next reaction to have a look at, let's say propanoic acid, and this time we'll pick a carbonate for our reaction, so let's say sodium carbonate rather than sodium hydrogen carbonate. If we watch this reaction, we now make the propanoate ion. We'll have a sodium ion that's attracted here to that negative charge, and we also need to make some carbon dioxide and water out of this reaction. So for this, you'll see some effervescence because you've got carbon dioxide gas being produced. Need to just ensure that we've balanced our equation as well. So we need 2 of these, and we're going to need 2 of these to make sure everything's balanced across the whole thing. Some more examples. So we could react with, say, magnesium. So if I just take methanoic acid again, and I put in some magnesium metal here, we just need to make sure that we're careful about the charges of the ions that are being made. So in this situation, the methanoate ion is going to be 1-, so we're going to need 2 of those for our 2+ charged magnesium. We're going to produce some hydrogen gas as well from that reaction, but we just need to make sure that we've balanced this reaction as well. So we've got 2 4 hydrogens there, we've got 2 hydrogens in this bit, another 2 there, so the hydrogens are balanced. We're going to need 2 4 oxygens in total, they're balanced, magnesium's balanced, and our reaction is complete. Now, you can include these charges in here just to show that you've got an attraction between 2 opposite ions, but it's not necessary, you don't have to show them in the reaction at all. So thank you very much for watching. Please remember to like and subscribe this channel, especially if you've enjoyed the video. Please share the videos as well. Keep on watching.